last time we looked at the extended fin example, and we used Dirichlet boundary conditions on both ends. So we had a temperature boundary condition on the left, temperature boundary condition at the tip. And I suggested that the tip boundary condition being specified as a particular temperature isn't very realistic. So let's look at a more realistic boundary condition. So we're going to have convection at the tip. So there'll be convection at the tip, just like there's convection around the rest of the fin. So this would be a more physical boundary condition. So for convection at the tip, basically what you have is a balance between conduction, so there's heat conducting out of the tip, and convecting into the surrounding air. So on the left is the conduction, that's using Fourier's law, minus k dt dx. So basically the gradient of the temperature drives the heat out of the tip of the fin. So that's the Fourier's law for the heat conduction side. And then all of that heat, so it's equal to, all of that heat has to be convected out of the tip into the surrounding air. So that's the H, the convection heat transfer coefficient, times the driving temperature, the temperature at the tip, minus the ambient air temperature. So in terms of U, which we introduced last time, U is just T minus T infinity. This is minus K du dx at the tip is equal to H times U at the tip. So what you'll notice is we have, rather than U being specified at L, so U of L is equal to some specified temperature, instead we have a linear combination of U and du dx being specified. So we no longer know U at the tip. We have to calculate it, as you'll see. So this is a specific form of the general, what's known as a Robin boundary condition. So we have Dirichlet, which we've seen, we have Robin, and then we'll also have Neumann boundary conditions, which are just a special case of Robin, as I'll mention in a moment. Or sometimes Dirichlet we call specified or fixed. Robin we call mixed, because both U and the derivative of U are a linear combination is being specified. So in any case, a general Robin boundary condition, which is what we have here, would be P times U plus Q times du dx is equal to R. And in this case, we're applying that at the tip. It could be at the base, or it could be, in our case, at the tip. So for the convection condition, P is H, Q is K, and R is 0. But we're going to use this general form of the Robin boundary condition so we can include other physics as well. So P times U plus Q times du dx is equal to R. And then the P, the Q, and the R are just constants that come from the problem statement itself. So this is how we deal with non-Dirichlet boundary conditions at one of the two boundaries. In this case, at the right boundary, where little I is capital I plus 1. So what we're going to do is, it's really a two-step process. We're going to apply the difference equation at the boundary. So we're going to set little I is equal to capital I plus 1. We had the difference equation in the previous video. So that gives us this expression right here. Now you'll notice I've highlighted in red the U capital I plus 2. I plus 2 is outside the domain. So the domain ends at x is equal to L, which corresponds to I is equal to capital I plus 1. Oh my goodness. And then the next point in would be capital I. But what we've done essentially is we've introduced a fictitious point, capital I plus 2. So this is not in the domain. We actually don't care what this temperature is. So we need to eliminate it. It's not even part of the problem. This is the boundary right here. So we need to find a way to eliminate this U cap I plus 2, the point right here. So to do that, this is the second step. So the first step is apply the difference equation at the corresponding boundary. And then the second step is to finite difference the Robin boundary condition, the Pu plus Q du dx is equal to R, and apply that at the boundary as well, at the same point. Little I is capital I plus 1. So we have P times U, so that's P ui plus 1, plus Q times du dx. And the second order accurate central difference approximation there would be U cap I plus 2 minus U cap I over 2 delta x, and then equal to our R. So what you notice, again I've highlighted in red, the boundary condition also includes this U cap I plus 2 term. So what we'll do is we're going to solve for that from the boundary condition, which is what you see here, and then we're going to use that and plug it back in to the u cap I plus 2 term in our finite difference equation. So let me just walk us through that. So here's our Robin boundary condition applied at the boundary. We solve for capital U, so little u sub cap I plus 2, which I've done here. That's just solving this for this term. And then substituting this in for u capital I plus 2 into our difference equation right here, the red term. When we do that, and we collect all the terms together, so everything times ui, everything times ui plus 1, everything that we know goes on the right-hand side, we get this expression right here. Now it looks complicated, but that's just because there's now more stuff times ui, more stuff times ui plus 1, and then more stuff that we know. But that's all it is. So then this equation we're going to append to our system of equations. So from the last time we had capital I minus 1 equations. Now we're going to add one additional equation to the end. We'll append it at the end, and that's going to be used to solve for u sub cap I plus 1, which is the temperature right at the boundary. So essentially what we've done is we've adjusted the coefficients, the a, the b, and the c coefficients correspondingly with the boundary condition. So that's all we've done. All right, so then the solution procedure is exactly the same as we had last time for the Dirichlet boundary conditions, except that we now have one more equation. That's the only difference. We'll still solve it using the Thomas algorithm. We just have one additional equation. If we did have a Neumann boundary condition, so Neumann is where you specify the gradient of the temperature, something like this. So du dx is being specified at the boundary. That's a Neumann boundary condition. So Dirichlet specify u, Neumann specify du dx, and Robin a linear combination of the two. In a heat transfer context, a Neumann boundary condition is saying, remember the Fourier's law, so the heat flux is being specified to be some value. So in our case, that would correspond to P being 0 and Q is equal to 1 in the Robin boundary condition. So again, a Neumann boundary condition is simply a special case of the Robin boundary condition. And then the heat flux, so for example, in the case where we are trying to draw heat away from a hot CPU chip or a hot chip using these extended fins, we'd like to know how much heat is being drawn away. So that's the heat flux from the base, so Q sub B. From Fourier's law, which we saw from the tip boundary condition, says that the heat flux from the base is minus K times the cross-sectional area at the base, so A sub C at 0, times the gradient of the temperature dt dx at the base. That's in terms of T. In terms of U, put in U is T minus T infinity, and you get this expression here. So this is the heat flux at the base. Now K is just a constant, A sub C at 0 is just a constant, so we need to evaluate the du dx. Now, of course, that's a derivative, so our first thought would be, oh, well, let's just use a second order accurate central difference. The problem is a central difference would use a point outside the domain. So instead, we have to use forward differences. So we'll use forward differences starting at the base and moving forward. So a first order accurate approximation, we've already derived this, for du dx at the base would be u2 minus u1 over delta x, and that is first order accurate. So that looks like this. So x is equal to 0, I is equal to 1, and it's using 2 points. I is equal to 1, and I is equal to 2. For a second order accurate approximation, so first order accurate is not enough for us, we go to second order accurate. That we derived also in chapter 7. That's the minus 3u1 plus 4u2 minus u3 over 2 delta x. That is now second order accurate, but it involves one more point. 1, 2, and 3. Now, we could also go to third order accurate. So third order accurate, we actually did derive this. That was in chapter 7 as well. And you get these coefficients, the minus 11 ui plus U1, plus 18U2 minus 9U3 plus 2U4 over 6 delta X. That is third order accurate, and it requires 3 points. 4. 3, 4. So that's the usual pattern. The higher the accuracy of the approximation, the more points are necessary. But you'll notice they're all forward differences. They all start from I is equal to 1 and increase to the right as we go into the domain. Okay, that's it for this short video on the convection boundary condition and heat flux. And now we're going to generalize this to how to look at second order boundary value problems.